For our project, we decided to figure out the science behind jumping fountains. Now, for those of you not familiar with what a jumping fountain is, here's a short video portraying what they do. As you can see, it is just a short burst of water from a pipe. Now, for our calculation, we used two variables, surface tension and laminar flow. For surface tension, we found that the radius of the column had to be less than 486 micrometers to hold the water together, which is pretty unrealistic. For laminar flow, we found that the velocity of the water coming out of the pipe had to be 128.03 meters per second. Any number greater than this would cause a turbulent flow, which would have water spewing all over the place. Anything less would hold the water together and keep it laminar, which is what we want.
So to perform these calculations, we first looked at surface tension. We found the surface tension characteristic of water to be 7.28 times 10 to the negative fourth newtons per meter. We multiplied this by delta H, the arbitrary height of a column of water. We set this equal to the weight force, mg, or in this case, rho g times the volume, delta H pi r squared. We wanted to solve for r, the radius of a jumping fountain that would allow for surface tension to keep a column of water in its columnar shape. Upon performing this calculation, we found that the radius has to be equal to or less than 486 micrometers to allow surface tension to perform the job we want it to. This number is much too small for a practical jumping fountain. Our next analysis consisted of a laminar flow. We used the Reynolds number, which characterizes that laminar flow occurs if the Reynolds number is less than 2300. Anything over 2300 will get into transitional and then into turbulent flow. Now, this equation is Re equals rho Vd over mu, rho being the density of water at 1000 kilograms per meter cubed, and mu being the viscosity of water, 1.002 Pascal seconds. To get the diameter of the jumping fountain nozzle, we searched for common design parameters of these fountains, and found the most common jumping fountain nozzle diameter to be 0.018 meters. Now, doing this calculation and solving for velocity, we found the velocity that would allow for laminar flow is anything less than 128.03 meters per second. This number makes much more sense than a radius of 486 meters and is a plausible explanation for the science behind jumping fountains.
So to conclude, from the surface tension analysis, the radius is too small for particle, so it is irrelevant. But from the laminar flow analysis, the value makes sense. It's fast, but so any number below that number will work for jumping fountains to work.